Section 4 of the review chapter is on rational expressions. A definition of a rational expression is the division of polynomials. When we had the section that included polynomials, we looked at adding, subtracting, and multiplying them, but we didn't look at division. So another way to think of this is a fraction that has a polynomial in the numerator and the denominator, such as x plus 2 over x minus 5. So that's an example of a rational expression. We could also have something like x squared minus 2x plus 3 over x cubed minus 1. Anytime we have a polynomial in the numerator and the denominator, it's a rational expression. One thing that we need to think about for a rational expression is the domain. When we've got a variable in the denominator, there's a chance that we could have 0 in the denominator, which is undefined. So 0 in a denominator is undefined. Like it means it has no meaning. Okay, such as we could just have anything. 305 over 0. It's undefined. That has no meaning. Okay, so the domain is the set of x values, or values that x can take on, or whatever the variable might be that's in the polynomial in the denominator, that make the rational expression defined. In other words, not the denominator not equal to 0. All right, abbreviation there, denominator not equal to 0. Okay, so to find the domain, so let's take a rational expression, x plus 5 over x minus 2, and find the domain, find the values of x that will make that defined. Okay, well, the values of x that are going to make it defined are the values of x such that x minus 2, right, the denominator, does not equal 0. All right, so we can just solve this for x. Okay, so that means that we get x, well, let's back up. All right, to solve that, we add 2 to both sides, right? And so we get x not equal to 2. Okay, so that is the domain. All right, it's all values except for 2. In set notation, we would write that as negative infinity up to, but not including 2. And then, in addition to that, we would have from 2, but not including 2, up to infinity. Okay, so a little review on interval notation or set notation there. If we want to go from the smallest number possible, we go from negative infinity as our starting point. And then our ending point comes after the comma, and if we're including it, we use a bracket, and if we're not including it, we use a parenthesis. All right, so that's a little bit of how we use the interval notation. Let's look at another one where we want to find the domain. All right, let's take 2 over x squared plus 5. Okay, so to find that domain, we said we take that denominator and we set it not equal to 0, and then solve for x. So if we subtract 5 from both sides, we get x squared not equal to negative 5. Okay, when we square anything, it becomes a positive number. And more specifically, if we square a real number, it's going to be a positive number. So what this tells us is that the domain is all real numbers, because there's no real number that we can plug in for x there and square it and get a negative. So the domain in words is all real numbers. In interval notation, we could write that as negative infinity to positive infinity. Okay, now let's look at simplifying rational expressions. So we want to think of this as like simplifying fractions. So if we have got common factors in the numerator and the denominator, we can cancel those out. Okay, so let's start off with this example of a times b plus 1 over a squared times b squared. Okay, we have got a common factor of a in the numerator and the denominator. So we can cancel a factor of a. So that means this a goes away and we're left with a 1. And in the denominator, if we cancel one of those a, that exponent of 2 becomes an exponent of 1. So this simplifies to b plus 1 in the numerator over a b squared. Okay, let's think about whether we can simplify any more. So we can only cancel factors in the numerator and the denominator. In the denominator, we have a factor of b. It's multiplied by a and another b. In the numerator, there is a b, but it is part of the factor b plus 1. That whole thing is a factor. The b by itself is added to the 1, so by itself in the numerator, b is not a factor. So this is our simplified rational expression. Let's look at domain. The domain is the values that the variables can equal before we simplify. So we got to look back to our original rational expression and determine which values a and b cannot be. Okay. All right, our denominator before we simplified is a squared b squared. We want that to not equal 0. Well, if a is equal to 0, that whole thing is 0. Or if b is equal to 0, that whole thing, a squared b squared, is equal to 0. So our domain is going to be a not equal to 0 and b not equal to 0. All right, let's look at another example. Let's look at 6 minus 3k over k squared minus 4. Okay, this at first look doesn't seem like we are going to be able to cancel anything or simplify anything, but we are going to be able to factor the numerator and the denominator, okay? And then factoring, we might get factors that are common to the numerator and the denominator. So in the denominator, in the numerator, we can take out a 3 from both those terms, and we're left with 2 minus k inside parentheses. So we have a factor of 3, we have a factor of 2 minus k. And that is over, we have a difference of 2 squares. So from our difference of 2 squares pattern, we know we're going to have k, and then 4 is 2 squared, so we have a 2 and a 2, and the signs are going to be a plus and a minus. It still doesn't look like we have like factors, but if we take out a negative 1 from the 2 minus k, a factor of negative 1 from the 2 and a factor of negative 1 from the negative k, that brings a negative 1 out in front multiplied by the 3, so we get a negative 3. And if we take a negative 1, let's start with the negative k. If we take a negative 1 out of negative k, that's going to be a positive k. And if we take a negative 1 out of a positive 2, we're left with a negative 2. So now over the denominator, we have a common factor of k minus 2. So those will cancel. And our simplified rational expression is negative 3 over k plus 2. Okay, domain. That is going to be based on the non-simplified rational expression. So we can either look at the before we factored or after we factored, and say we want the denominator to not equal 0. Okay, so maybe a little refresher here on how we solve something like this. Well, we can add 4 to both sides, and then take the square root of both sides. Okay, we got to remember, if we introduce a square root to a number, we have to take the plus or minus case. So what we get here is, that should be not equal. So what we get here is k not equal to 2 or negative 2. And if we look back at that denominator, we can tell that that really is the case. If we take 2 and square it, we're going to get 4. Subtracting 4, we get 0. If we take a negative 2 square it, we get positive 4. Subtract 4, we get 0. So that is the domain for that rational expression.